Okay, let's do problem 21 in chapter 2 on page 40. And here's the problem. It says a car accelerates from 13 meters per second to 25 meters per second in 6 seconds. What was its acceleration and how far did it travel in this time? Assume constant acceleration. And I've already got it set up here with given, find, and solve. And somebody borrowed my calculator. Can you return it, please? Yeah, just put it right here. So, and I like to draw a little sketch of the problem. Here's the car. Its initial velocity is 15 meters per second. Then 6 seconds later, its final velocity is 25 meters per second, and we're assuming constant acceleration. So what are we trying to find? Well, it says, what was its acceleration? And how far did it go? We'll just call it delta x. Now, I want you to use the kinematic equations that we went over. And what do we know? We know initial velocity, final velocity, time, and we're trying to find acceleration. So let's ignore delta x. What's the equation that doesn't have delta x in it? Because we don't know delta x and we're going to find it, but we're going to find it later. And that would be the first kinematic equation. Then we're going to solve for acceleration. Well, this is v minus v naught. And then we're going to divide by time. Now this is also equal to delta v over delta t. It's the same thing. So you can start with this definition of acceleration, or you can use the first kinematic equation, but it'll get you the same place. And now we can plug in our values. 25 meters per second minus 15 meters per second divided by time, which is 6 seconds. And, oh wait, I did something wrong, didn't I? This is 13, not 15, I'm sorry. The initial velocity was 13. All right. Hey, when I'm recording like this, correct me if you see me making a mistake. It's cool. Just correct me. Now this 25 minus 13, that's a change in velocity of 12. We increased our velocity by 12 meters per second. 12 divided by 6 is 2 meters per second There's my answer. Or 2 meters per second squared. But you got to get the units right to get full credit for that answer. Then we want to find delta x. Well, what if now I could use pretty much any kinematic equation that has delta x in it because I've got the acceleration. But what if I didn't have the acceleration? Or what if I made a mistake in calculating the acceleration? I don't want to carry that mistake forward. So what's the kinematic equation that doesn't have acceleration in it? If you look on the little chart that we made for the lecture for this, it's the second one. That is delta x equals v naught plus v divided by 2 times time. That's the second kinematic equation. And so now v naught is 13 meters per second plus the initial or the final velocity was 25 meters per second. We're going to divide that by 2, and then the time is 6 seconds. So see if I can do this on my other 2. That's 3. What's 13 plus 25? That's 38. Is that right? And then 8 times is 24. 24 9 is 2 is 11. So it's a delta x should have been 114 meters. Okay. Now, some of you, when I was looking at your solution for this, some of you got delta x in a very clever way. You graphed it, you know, the velocity is a function of time, and you went velocity and time, and you did this, start off 13, goes up to 26, and then you calculated the area underneath here and underneath here. You know, you put numbers on it, and you got the right answer. That's really good. Remember that this equation right here, to get delta x, well, this is the equation for the area of a trapezoid, right? A trapezoid. And look, there's a trapezoid, right? You know, the average base times the height. Let's try to turn it like that, though. Average base times the height. That's what this equation is. Okay? Any questions on this problem? Yes?
For like the summary part, do we just mention for like the summary part, we just like say what we got wrong, what we got right?
Yeah. Yeah. That is all.